Bismillahirrahmanirrahim. Assalamu alaikum. Today we are going to start Article 6.2, which is about line integrals, and we'll discuss line integrals in plane, space, and vector fields in this section. So first of all, what is line integral? Line integral is similar to a single integral, except that instead of integrating over an interval AB, we integrate over a curve C. So just as for an ordinary single integral, we can interpret the line integral of a positive function as an area. So this is how this area looks like. In fact, if fxy is greater or equal to 0, so line integral over the curve C, fxy ds represents the area of one side of the fence or a curtain. Whose base is the curve C, okay, and whose upper part comes from the heights, that is the value of fxy at some point xy on the curve C. So such integrals are called line integrals or curve integrals sometimes. So they were invented in early 19th century to solve the problems involving fluid flow, forces, electricity, magnetism. So first of all, in order to solve such integrals, we have to convert C into parametric form, right? So we have to find the parametric representation of the path C. That is, x equal to xt, y is equal to yt type equations are required, where t lies between a and b. So in this way, actually, we map a curve onto an interval, right? So for every point t in the interval, there is a point xy on the curve C. So this is a mapping from a curve to an interval. Uh, so equivalent to C can be given by the vector rt is equal to xti plus ytj. So this is the parametric equation. So this is the vector equation of the curve C. So we assume that C is a smooth curve. Smooth means that is our derivative of r is continuous, and our derivative of r is not equal to z at any point in the interval. Not equal to 0 at any point in the interval. So let's divide the parameter interval AB into n subintervals ti minus 1 ti of equal width. So we let xi is equal to xti and yi is equal to yti. So the corresponding points P, X, I, yi, that is ith point on the curve Pi with the coordinates xi, yi, divide Ci into n sub arcs with the length delta S1, delta S2 up till delta Sn. So here is the interval AB, and T belongs to this interval. So if this is the point ti minus 1, so corresponding to this point, there is this value of the t, there is a point pi minus 1 on the curve, okay, whose coordinates are xti minus 1, yti minus 1. Similarly, if we have this point ti, there is a point corresponding to this value of t, which is pi, okay. And similarly, if we have ti star, a point lies in this sub-interval, then there is a point on the curve pi star with the coordinates xi star, yi star. Okay. So now, what we are going to do? We are going to find the values of f at xi star, yi star. That is at all such points pi star. So we are going to find the values of f, and then we multiply the length of the subarc delta si like this, and then we add all these products similar to Riemann sum. And then in limiting case, this will become the line integral of fxy, right? So this is the formula for or definition, you may say, definition of line integral of fxy with respect to ds is equal to sum of all these products as n approaches to infinity. and of course provided this, if this limit exists. So now, in order to find the value of ds, we have to recall a formula of arc length from calculus 1, which we learned in semester 1. So L is equal to integral from a to b dx by dt square plus dy by dt square dt. So this is the parametric representation of the arc length. So we will replace this ds by this. X will be replaced by xt, y will be replaced by yt, where xt and yt are actually parametric representation of this curve C. Okay, so evaluation of these line integrals is very simple. So I will discuss in later slides. So this is the formula. So after plugging in all the values, this is the formula you need to remember to solve or to evaluate this integral. So this formula can be used to evaluate the line integral from a to b, xt yt into square root of dx by dt square plus dy by dt square dt. This is actually the value of ds, and x is replaced by xt, y is replaced by yt. So this is the parametric form of the curve, and a, b are limits of t. T lies between a and b. So there is therefore lower limit of t is a and upper limit of t is b. Actually, the whole whole integrand is transformed into t, into one variable. Okay, so initially we had two variables. Now there is only one variable, and we have single integral, and we know how to solve it. So this is formula 3 in the book, just for reference. Okay. So the value of the line integral does not depend on the parameterization of the curve, provided the curve is traversed exactly once at t increases from a to b. So the challenge here is how to transform the equation of the curve into a parametric form. So we'll learn it by doing a few examples. So in special case where C is the line segment that joins A0 to B0. Okay. Now you can see that y is not changing in this case. Y remains constant and y remains actually 0. Where a is where x is changing, where x changes from a to b. So using x as the parameter, we can write the parametric equation of C as x is equal to x. Okay, x is equal to x, where x lies between a and b, and y is equal to 0. So since y remains constant, so we can use this parametric form, or you can use this parametric form: x is t, y is equal to 0, where t lies between a and b, one and the same thing. And in this way this line integral will become a single integral like this. Okay, so y is 0, x is x, so ds becomes dx, and this is the line integral to solve the. So just as for an ordinary single integral, we can interpret the line integral of a positive function as an area. I have just told you. Let's see how to evaluate the line integral using the formula we have just learned. So this is the line integral we have to evaluate over the curve C, which is upper half of the unit circle x square plus y square is equal to 1. Now fxy here is 2 plus x square y. So first of all, we have to find the parametric equation of C. Okay, so first step is to find parametric equation of C. Now this is a circle, so in this case this is easy. This is a circle, unit circle with center 0 0, that is origin. So parametric equation of this circle is x equal to cos t and y is equal to sin t. And since upper half of the unit circle is C, so limit from of t, so is 0 to pi. Okay, so the upper half, it looks like this. So for upper half,
theta starts from 0 and theta ends at pi. Okay, so theta here is t. So t lies between 0 and pi. Okay, so rest is quite easy. So now we have limit, we have to change, we have to transform this function into t, and we have to plug in the value of ds in terms of t, and we have to integrate this single integral, and we'll have this answer. You can do it and try it yourself. This is actually example number 1 in your book. Okay, next, piecewise smooth curve. Sometimes we have a collection of curves, right? uh, and the whole curve is not smooth, because there are some points where derivative is not defined like this. This is a union of 5 curves, c1, c2, c3, c4, c5. Rather, I must say this is the union of 5 smooth curves. Now these are the points where this path loses the smoothness, because derivative is not defined at these points. Okay, so in this case our line integral will be splitted into the sum of the line integrals. So we will first find the integral along this line, then integral along this line of the same function, of course, then integral along this line, then along this line, and then along this line, and then we'll add them up to find the value of the integral along c. Okay, so there is an example of such type of curve. Evaluate integral of 2x along the c, where c consists of the arc c1 of the parabola y is equal to x square from 0, 0 to 1, 1. So this is the arc of parabola from 0, 0 to 1, 1, and followed by the vertical line segment c2 from 1, 1 to 1, 2. Now we have to evaluate this integral along c1, and then we have to evaluate it along c2, and then we'll add both of them to find the value of this line integral. So first of all, c1. Now target finding parametric equation of the parabola y is equal to x square. So in this case, again, you can say x is equal to x and y is equal to x square, where x lies between 0 and 1. Okay, from 0, 0 to 1, 1, x lies between 0 and 1. Or as I said, you also can write x is equal to t, y is equal to t square. This is also parametric form of the parabola, where t lies between 0 to 1, right? So now this is up to you. Whatever you find easier, you can do it. Okay, so along C1, we have this parametric equation, and this we have limits for parameter 0 to 1, 2x as it is. So this is the value of ds, because in this case our parameter is x. So dx over dx plus dy over dx square, and parameter is dx. So here parameter is x, so you can find dx here. Otherwise, it would have been dt. Okay, and rest you can just integrate it as a single integral. So we have this answer. Along C2, this is interesting. Along C2, x is constant, and x remains 1 throughout the line. Okay, so x is 1, y is equal to y, or you can write y is equal to t. Uh, x is equal to 1, y is equal to y. Now, what is the limit of y? Y lies between 1 and 2. Okay, so this is the limit for y. Y lies between 1 and 2. So for C2, our parameter is y. So we have to convert all the integrand into y. So x is 1. So we plugged in the value of x as 1. And since parameter is y, as I said, dx by dy, dy by dy. And this dt is replaced by dy, right? And rest is the matter of calculation, and you can evaluate. Now final step, this integral of 2x ds along the curve c is equal to integral along c1 plus integral along c2. So this is the answer. Okay, the line integrals application. So physical interpretation of the line integral depends on the physical interpretation of the function. So initially I said it represents area, but if a function represents a linear density at a point xy of a thin wire shaped like a curve C, then this integral, line integral, represents mass of the wire. And we can also find, using this line integral, the center of mass, which is the point x bar y bar, where x bar y bar can be represented by these line integrals. Okay, another type of line integrals, uh, two other line integrals are obtained by replacing delta Si in definition 2 by either delta xi or delta yi. Okay, so let me show you what was the definition 2. So this was the definition 2. Initially we defined the line integral as sum. Okay, so this is the definition 2. If we replace ds I by delta Si by delta xi or delta yi, so the resulting integrals will become the line integrals of f along C with respect to x and with respect to y respectively. Okay, so how to distinguish between these integrals? So actually, to distinguish the original integral from these integrals, these are actually given in equation 5 and 6 in the book. So 5 and 6, we call it the line integral with respect to arc length. So this is the line integral with respect to arc length ds, and this is the line integral with respect to x, and this is the line integral with respect to y. Okay, now in order to solve these integrals with respect to x and y, we again need parametric form: x is equal to xt, y is equal to yt. So dx will be replaced by x prime t dt, and dy will be replaced by y prime t dt. So this way the line integral with respect to x can be written as integral from a to b, where t lies between a and b. So integral from a to b, f of x t y t, x prime t dt. Dx is replaced by x prime t dt. And integral of line integral of f x y with respect to y can be written as integral from a to b, f of x t y t, y prime t dt. Okay, so dy is replaced by y prime t dt. It frequently happens that the line integral with respect to x and y occur together. So if they are there is a situation that we have a line integral with respect to x plus a line integral with respect to y, we can write and along the same curve, this is the point to be noted actually, along the same curve, then we can write it as a single integral along the curve C, pxy dx plus qxy dy. Alright. So when we are setting up a line integral, sometimes the most difficult thing is to think of a parametric representation for a curve whose geometric representation is given. In particular, we often need to parameterize a line segment. So for this you need to recall the equation of line, vector equation of line. So here we go. This is the vector equation of line. So it is useful to remember that the vector representation of the line segment that starts from R0 and ends at R1. And we learned this in, again, calculus 1 in semester 1. So RT is equal to 1 minus T R0 plus T R1, where T lies between 0 to 1. So this is very important. T lies between 0 and 1. So let's use this formula to evaluate a line integral. So here is the line integral. This is example 4 of your book. You can read from there too. So evaluate this line integral y square dx along the curve C plus x dy, where part A, C is equal to C1. C1 is the line segment from minus 5 minus 3 to 0 2. So first of all we have to find the parametric form of the line. And part B is along C is equal to C2, that is along this curve, the arc of the parabola x is equal to 4 minus y square from minus 5 minus 3 to 0 2. All right. So let's start with part A first. So what is the equation of the line? So let me try here to just make sure that how does this come. Since we have r naught minus 5 minus 3, r1 is equal to 0 2, right? So our formula is r is equal to 1 minus t r naught plus t r1. Just plug in all the values. This is r is actually x y vector, and in position vector of any point xy. So 1 minus t, this is a scalar, and r naught is minus 5 minus 3 and plus t, r1 is 0 2. Okay, so let's simplify it. We have minus 5 plus 5t. Okay, this is the first vector. Minus 3 plus 3t, all right, plus 0 2t. So by adding both the vectors, we have 5t minus 5, and y component is 5t minus 3. Okay, so xy vector is equal to this. So that is why x is equal to 5t minus 5, y is equal to 5t minus 3. So this is the parametric equation of the line, and where t lies between 0 and 1. So limit for t is 0 to 1, and just plug in all the values. So we have and evaluate this single integral. We have the answer minus 5 over 6. Now along the path, the parabolic path, minus 5 minus 3 to 0 2. So again, a parabola is x is equal to 4 minus y square. You can say y is equal to y and x is equal to 4 minus y square, or you can say y is equal to t, x is equal to 4 minus t square. It's up to you. So y lies between minus 3 to 2, because we are starting from minus 3 and we are ending up to 2. So rest you know how to do it. Just plug in the values and you have the answer. Now just keep it in mind, dx will be replaced by derivative of this into dt. So 5 dt. Okay, you can see here 5 dt. Okay, dy is also 5 dt. So dy is 5 dt. In this case, our parameter is y. So everything is going to be changed into transformed into y. So dx is in fact minus 2y dy. See, and dy is dy. Okay, so I hope it is clear, and limits are also obvious. Minus 3y varies from minus 3 to 2, and then evaluate it, integrate it, and plug in the limits. You have the answer. So arc length. Notice that we got different answers in parts A and B of example 4, right? Although the two curves had the same endpoints. Thus, in general, the value of the line integral depends not just on the endpoints of the curve, but also on the path, right? However, in next sections we can see sometimes the answer is independent of path, but in this case answer is not independent of path. For different paths we have different answers, although initial point and terminal point is same. Also notice that the answer in example 4 depends upon the direction or orientation of the curve. Okay, so orientation of the curve is also important, as x varies from left, x increases from left to right, y increases from up to down. So there is always a positive orientation for every path. So we learn this by doing some practice questions. Okay. So in general, a given parameterization x is equal to xt, y is equal to yt, where t lies between a and b, determines an orientation of a curve c with the positive direction corresponding to increasing values of the parameter t. Okay. So as t increases, uh, in the direction in which t increases is called the positive orientation. In short, you may say. So the initial point A corresponds to the parameter value. So in the initial point A corresponds to this point, and initial terminal point B corresponds to this point. And minus C actually denotes the curve consisting of the same points as C but with opposite orientation. Okay. So this is actually similar concept to the intervals we have already learned, and you you are already familiar with. So however, if we integrate with respect to arc length, the value of the line integral does not change when we reverse the orientation of the curve. This is because delta Si is always positive, whereas delta xi, delta yi change sign when we reverse the orientation of C. Okay, we now suppose that C is a smooth space curve. So next topic is line integrals in space. So far we discussed line integrals in plane. Okay, so now line integrals in space. So suppose that C is a smooth space curve given by the parametric equation x is equal to x. So since this is space, so there must be another parameter which is not written here. X is equal to xt, y is equal to yt. So let me write third one as well. This is somehow missed. Z is equal to zt. So this must also be included. So in vector form, rt is equal to xti plus ytj plus vtk. So we are in space. So vectors, 3D vectors looks like this. So suppose f is a function of three variables that is continuous on some region containing C. Then we define the line integral of f along C in the similar manner as we defined in plane. So this is the definition of the line integral in space, and this is the formula to evaluate the line integral in space. So in this case ds becomes this, and of course there is dt as well, which is again missing. So let me write, okay, dt, and this is another representation, and this is another representation. This is a special case actually when fxy is equal to fxyz is equal to 1. So this becomes integral with respect to arc length, and this is in fact the total length of the arc. Okay, this integral will give us the length of the arc or length of the whole curve. All right, line integral in space continues, and there are a few examples in your book, and I'll urge you to do them yourself. I'm not going to discuss here, although they are given, but this is example number 5. You have to do it yourself. Example number 6. So please do it yourself. So the same idea. You have to find the parametric form of the curve, and then transform everything into the parametric form, and apply the limits in order to convert actually the line integral to the single integral, and then integrate it and plug in the limits, and you have the value. So these are the examples, and these are given in the book. Okay, next line integral of vector fields. So work done by a variable force Fx in moving particle from A to B along the x-axis is defined by this formula. W is equal to integral from A to B Fx dx. This is the work done by a variable force Fx. Okay. uh, Next formula. So in order to establish the line integrals of vector fields, let's go through few results. So next concept, the work done by a constant force in moving an object from a point P to another point in the space is F dot D, okay, where D is PQ. The particle moved from point P to the point Q, okay. So PQ is the displacement vector. So let me write here Q, P to another point Q, okay. So since F is force in 3D, so its vector representation is Pi, Qj, Rk. So PQ are the components. In R cube we are discussing the vector, so this is the vector form of the force. And finally, what we actually need to learn is, you can read all this stuff from the book, but you have to remember the formula. We will discuss it tomorrow in detail. Yes, this is the formula. F dot dr. If we are required to find the total work done uh, by the force, so this is the formula, F dot dr. Okay. So here is an example of find the work done. Find the work done by the force field F xy is equal to x square I minus xyj in a moving particle along the quarter circle. RT is equal to cos ti plus sin tj, where t lies between 0 to pi by 2. So work done is F dot dr along the path C. Okay. So since x is equal to now along quarter circle, so path is here quarter circle, C is quarter circle. Okay. So R here is cos ti plus sin t j, that is the vector along the path, cos ti plus sin t j. So what is the formula we just saw? That formula is F dot dr, integral of F dot dr along the path C, along the curve C. So uh, application is very simple, evaluation is very simple. So we just have to convert F into parametric form. So parametric form of F is this: x square is replaced by cos square t, xy is replaced by cos t sin t, and this is the F, and r prime t, because dr is r prime t dt. Okay, r prime t dt. So dr is equal to r prime t dt. So this is just like differential. Okay, if you have a function y is equal to fx, so dy is equal to f prime x dx. So similarly, dr is equal to r prime t dt. So r prime t is given by this uh, equation. So rest is just plugging in the values and evaluating this single integral. So answer is minus 2 by 3. Okay. So that is all. We'll discuss the last part tomorrow in detail, and we'll practice few more questions, and I'll urge you to read the article in the book as well after listening the video and after watching the video. Okay, thank you, bye bye, see you, Allah Hafiz.